3x plus 2. The rate of change, the up and over, is based on the graph. So if I come in here, and this is not in your textbook, so that's why you really need to write this down, because you won't find it again in the textbook. Okay? So I'm going to plug this in my calculator. So this is a simple linear equation, right? It's just 3x plus 2. I'm going to come over here and look at the table. And so we'll just plug in some numbers. So 1, 2, 3, 4. And that'll give me 5, 8, 11, 14. Now there is a constant rate of change. And what a constant rate of change does is when I look at the graph, it graphs as a straight line, okay? So if let me put this in a standard fit, it's a straight line because the rate of change is the same every time. And we know from our algebra experience that that rate of change is 3. In other words, the slope, but now I'm not going to call it slope anymore, I'm going to call it the rate of change, is 3 over 1. That means I'm going to go up 3 and over 1 to get from one point on the line to the next. Now I can verify this quantitatively by looking at the values of the equation. If I go from 1 to 2, in other words, if I'm going to look at delta y over delta x, if I go from 8 to 5 and 2 to 1, I'll get 3 over 1. If I do that again, and I say 11 to 8, 3 to 2, I'll get 3 over 1. And if I did that for every one of those terms, I would get that. In fact, if I came in here and I looked at that, for every change in x, in other words, what I'm getting, really where this is coming from, is that what I'm saying is, to get from here to here, I add 1. That's where this 1 comes from. To get from here to here, I add 3. That's where this 3 comes from. And it's the same every time. I add 1 to get from this one to this one. I add 1 to get from this one to this one. I add 1 to get from this one to this one. Here I add 3, and here I add 3. So it's a constant rate of change. Does that make sense? Yeah. Now here's what's different. If I change this to y is equal to 3x squared plus 2, and I do the same thing and I make a table of values, and I go 1, 2, 3, 4, now it looks different. Now it looks different. So now I'm going to plug that in for an equation, and I'm going to put them side by side so you can see the difference. So here I'm going to say 3x squared plus 2. But if I look at the table of values, when x equals 1, this one still equals 5, right? But now I've got 5, 14, 29, and then 50. So that one changes drastically, right? Here, I want to point out, here though I go plus 1, plus 1, plus 1. On the right hand side, it looks different though. Here I go, what do I add to get from 5 to 14? 9, plus 9. What do I do to get from 14 to 29? 15. What do I do to get from 29 to 21? So what do you notice about those? So my rate of change is changing.
By 6.
By 6, that's true, but what is changing it? So that's the thing. Now what would be nice is if I could represent that some way. Okay? What I could say is that, and you guys don't know this, and this is what we're going to ramp up to, Mr. Adams happens to know, what would be nice is if I could represent the rate of change as a variable of my rate of change of x, right, of x. If I could write an equation that would represent the rate of change. Well, that rate of change, what we call a derivative, is actually 6x. And it's no accident. We add 6, add 6, add 6. And if we were to go through this long process, what we kind of covered yesterday, and we'll do it again, we would end up with 6x. And this equation of 6x would represent this rate of change every time. Does that make sense to you guys? Now, eventually, we'll determine the rate of change of something even more complicated. So if I were to take this and do something like y equals 3x cubed plus 2. And I'm really keeping this simple. If I were to do the same thing, it would change even more. So let's plug that in. Let's do 3x cubed. And I'm just going to change this one to a 3. And I'm going to hit second graph. And so now for that one, that was in y2, right? Again, my change in x is always going to be plus 1, plus 1, plus 1. But now my numbers are 5, 26, 83, and 194. Now it gets a little more complicated, but I will tell you this, that our rate of change, and you haven't figured this out yet, is 9x squared. So as I change from this to this, what do I add to 5 to get to 26? 21, right? What do I add to 26 to get to 83? What was that? 57. What do I add to 83 to get to 194?
111.
So now it's really, really complicated to kind of figure out what we're doing. Okay?
How do you know that the rate of change is 9x squared?
Well, I have to teach you that, and it'll take me about 2 months.
Oh.
But this is what we're ramping up to. Okay? That's what we're ramping up to, is we're trying to figure out a way to represent this rate of change as an equation. Because everything's dependent upon x, because x is the independent variable. And so based on the math, I'll tell you this 9x squared is no accident. It comes from this original equation, and it's based on the limits as h approaches 0. So we really got to understand these limits as h approaches 0. So what does that look like graphically? Well, graphically, going back to a simple equation here, when we go to do this limit thing, I said that we could probably find that as a function of x. So let's go back and look at this. We could find that as what we're really looking for is the slope of the tangent line. Now, this right here, this blue line, is a secant line. Now, secant means that it is going to have 2 points of intersection. Okay? So, what I notice is, if I move this point here all the way to 0, what is the slope at that point in time? 0. We know that because it's a minimum that the slope is 0. The tangent line. A tangent line intersects the curve at only one point, right? So we know that at the point 0, 0, the tangent line or the slope should be 0. However, I cannot plug in the same point twice. In other words,
That's not right.
no, it's not right. In other words, I cannot go in here and say m, which is y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. I can't pick the same point for this. It won't work. So in other words, I can't say that this is x sub 1, y sub 1, and I can't say this is x sub 2, comma, y sub 2. Whoops, this should be 0. Y sub 2. Because when I plug it in, I get 0 minus 0 0 minus 0, right? And so then I have a 0 here in the denominator, and that's what really messes it up. So this is with numbers, right? So now let's pick out another spot. Maybe 0 is the issue. So if I go back and I pick out another spot, let's say you guys will pick, we'll pick 1.5. So I've got 1.5 comma 0.5, or a little bit less than that. Well, let's pick an even number. Let's pick an integer. 2, and I'm not quite sure what this function is, but it looks like 2 and 0.75, maybe a little bit more than that, 0.8. So if I pick the 0.2 comma 0.8, right, and then I pick that same point, because that's what the tangent line is, right? The tangent line is when they're on the same point. See, I have a very thin purple line, and that's the tangent line. That's what it should look like. So if I pick 2 points, 2 comma 0.8 and 2 comma 0.8, and then I graph those, or I try to find the slope. In other words, I'm going to let this information here, this is x sub 1, y sub 1, x sub 2, y sub 2, and if I wanted to calculate the slope at that instant in time, I can't, because I end up with 0.8 minus 0.8 all over 2 minus 2, which is 0 over 0. And you say, well, that's not fair, Mr. Adams. It won't work. But if I move a little bit away, let's say I move over to 3. Now if I choose this, what do you notice about the blue line, which is the slope, or the line, the secant line versus the tangent line? In other words, look at this blue line and look at this purple line. The purple line is the one that I want to calculate the value for. I want the slope of this purple line, which is the tangent line. It only intersects my graph when x equals 2 one time. Now I can calculate this value, right? I could arbitrarily choose that value. It looks like 327. And so in other words, I could say, if I were to do this again, I could calculate the slope of that and approximate it. I could say that the slope is equal to y sub 2 minus y sub 1 all over x sub 2 minus x sub 1, and I could choose the 0.2 comma 0.8 and the 0.3 comma, what did that look like to you guys? 1.75 maybe? And so I could plug that in. I could plug those values in, and I would get 1.75 minus 0.8 all over 3 minus 2, and I get something over 1. What is that? I should have made it 1.8. That would have made it easier. What is that? Is that 0.95? Is that what that is? But that's just between those 2 points. So if I look at this thing, my blue line is too steep. That number that I calculated is steeper than the purple line. The slope of the blue line is more than the slope of the purple line, and I want the purple line. The problem is, what do I got to do to get closer to the purple line? I've got to move in closer. I got to make the points closer to each other. Well, the distance between the 2 points is h. So what do I need to make h do? Get smaller. Really small. Now here's the thing. What if I represented those in a different way? This only works when x equals 2. In other words, all this math that I'm going to do will only work for x equals 2, and I will make this smaller and smaller and smaller. In other words, what I said was I had 2 comma 0.8, and over here what I really had was 2 plus 1 comma 1.75. And if I really wanted to be fancy about it, I could say that this is 2 comma f of 2, the function evaluated at 2, and I could say that this is 2 plus h comma f of 2 plus h. I could have written it like that, couldn't I have? Now pause. That's where we lose everybody. What's h? Well, that's what we'd like it to approach, but based on what I did, I said h was 1. Ultimately, we want h to approach 0.
I thought h was always 0.
No, we want it to approach 0, but what we're trying to do is back up a little bit and understand why we want it to approach 0.
So like, could you have 3 plus h instead of
No, because we're interested at what it is when x equals 2,
Okay,
right?
yes.
I suppose if I wanted to generalize this, I could say it something like this. Couldn't I say that this is x, comma, f of x?
Yeah.
And then the second point would be x plus h, comma,
F,
f of
F,
x plus h. That's what I'm ramping up to, okay?
Can you just always claim?
Well, yeah, that's what we're going to call it. So now if we have it written like this, and I want to take the slope, if I take the slope using this sort of notation, I would say that the slope is equal to the y value, the second y value, which is f of x plus h, minus the first y value, which is f of x, all over the second x value, right, which would be x plus h, and then minus my x. And then as you guys already figured out, and we kind of went over this yesterday, the x's cancel. And so what we're really saying is that the slope, and this is all based, no numbers, just variables, my slope is going to be at any instant in time x plus h minus f of x all over h. Okay? But now I can choose h to be anything I want it to be, right? I can choose h to be anything I want it to be. So if I come in here and I look at my graph, I notice that when h is a really big number, what happens to the blue line with regards to the purple line? In this particular case, they separate, right? So if I bring that closer to my h value, what would happen? Well, as I bring, in other words, as h gets smaller and smaller, notice that the blue line gets closer and closer to the tangent line. So to make my secant line come closer and closer to the tangent line, what should h approach? 0. And I can't say that h equals 0, because if I say h equals 0, then the equation is wrong, right? So I can't say that h equals 0, because if I do that, this whole thing's bonkers. But what I can say is, as soon as I find my marker, that I could take the limit of this as h approaches 0, and I can get a pretty good answer. Okay? Does that make sense to you guys? Okay.